A wayward satellite of mass 1,500 kilograms has developed a highly elliptical orbit around the Earth. At its closest approach, its perigee, it is just 500 kilometers above the Earth's surface. Its furthest point, the apogee, it's 3,000 kilometers from the Earth's surface. The Earth has a mass of 6 times 10 to the 24 kilograms and a radius of 6.4 times 10 to the 6 meters. The gravitational field strength of the Earth is shown in the graph. Okay, so hopefully you can all see that graph in your books there. So the radius of the Earth is that horizontal line to the left there. And we have an area under the graph between our perigee and our apogee. Okay, calculate the change in potential energy of the satellite as it moves from the closest to the furthest point from Earth. So we need the area under the graph between our closest point and our furthest away point. Okay, so between the perigee and the apogee. So again, we need to count up our squares. So I make it 1, 2, 3, 4 times 6, 7, 10, 11, 12. So I've got 48 there. 51, 52. I make it 26. I make it 26. So see if you get something close to that. Oh, 26? That can't be right. But I mean 46. No. 48. I do mean 76. That sounds much better. Yeah. Okay, so there's 76 squares. Again, let's work out what each one is worth. So each square is worth, so along the bottom is 0.2 times 10 to the 6. 0.2 times 10 to the 6 along the bottom. And the side is worth, it's just 1. That's easy. 1 Newton, what is it? Newtons per kilogram. Okay, so each square is, let's write this a bit neater. So each square, the area, is 2 times 10 to the 5. Newton meters per kilogram. Okay. And so you see our square has in it per kilogram, which is why we need to take our mass into account. So 76 times that would give us 152, so 1.52 times 10 to the 7. Is our total area under the graph. Area total.
So what it is J kg to the big one?
Yes. Yep, Newton meters are the same as joules, absolutely. Okay, so there we've got 1.52 times 10 to the 7 Newton meters per kilogram. But again, we need to multiply by our mass to get our total change in energy. So our mass is 1,500. And so, to get our total energy change or our total work done, it's going to be 1,500 multiplied by 1.52 times 10 to the 7. Okay. 2.28 times 10 to the 10. Yeah.
I was confused because it says that the area under the graph is the energy change, and that also change in potential energy.
Yep.
So why would you have to calculate the work?
Because the area under the graph of that type of graph, of gravitational field strength against distance, is not the total potential energy. It is the energy per kilogram of mass. So this gives us, for every kilogram of mass, we have that much energy change. So we have 1,500 kilograms worth of mass. So to get the total energy change, we have to multiply the amount of energy per kilogram by the amount of kilograms. Does that make sense? Okay. Yeah, so just remember, if you have a gravitational field strength against distance, you need to multiply by the mass. Okay, next. I like this question. This would be a good exam question, to be honest. The satellite was moving with a speed of 15 kilometers per second at its closest point to Earth. How fast was it traveling at its furthest point? Good question. So what is the key point here? How are we going to start to work this out? What's the key idea? Why is it going to change speed? Good. What happens to that potential energy? To? Kinetic energy. Good. So we are losing gravitational potential energy and it's being converted to kinetic energy. So we can see that this is the amount of work done. This is the difference in our gravitational potential energy. That must also be our difference in kinetic energy. Okay? All of that gravitational potential will be converted to kinetic. So the first thing we need to do is work out, well, I guess the kinetic energy at this 15 kilometers per second, and then we can subtract this change. All right, so our kinetic energy traveling at 15 kilometers per second is 1/2 times mv squared. So our mass is 1500. Our velocity be 15 kilometers per second, right? 15,000 meters per second squared. So it's not kilometers per hour, so we don't need to do that 3.6 thing. It's kilometers per second, so it's 15,000 meters per second. So I get 1.69 times 10 to the 11. So that is its total kinetic energy when it's at its closest point to Earth. So if we move it further away from Earth, we are giving it gravitational potential energy, so therefore we must be taking away its kinetic energy. Okay? So to work out its speed, we need to subtract this change in energy from its kinetic energy. Okay? Now, you might be a bit confused why we're subtracting and not adding. Just think about it. Our satellite is moving further away from Earth. So as we move it further away from Earth, we are increasing its gravitational potential energy. Our EP goes up, so therefore our kinetic energy must go down. Okay, so we have to subtract our work done, we have to subtract this change in energy from our kinetic energy. All right, someone's got a better calculator that they know how to use scientific notation on, because I do not on this thing. That'd be great if you could figure that out for me. 1.69 times 10 to the 11 minus 2.28 times 10 to the 10. Anyone got it?
1.46.
Thank you very much. It sounds about right. 1.46 times 10 to the 11. So that is its kinetic energy at its furthest point. Okay? It's lower than its kinetic energy at the closest point, which we would expect. It passes the common sense test. So now, we need to figure out how fast it's traveling. We've got its kinetic energy, we've got its mass, we should be able to work out how quickly it's traveling. Okay, so remember, we can rearrange this equation. If you have trouble rearranging this equation, you could just put it straight into your cheat sheet as the rearranged version. So 2ek on m square root will give us our velocity. Okay, those two equations are just rearranged. So our velocity is going to be equal to 2 times 1.46 times 10 to the 11 over 1500, all of that square root. And what we are hoping for is to get something less than 15 kilometers per second.
13.94.
Good enough for me. So if that's 15 kilometers per second, yeah, I'll say 13.9 kilometers per second. And that makes sense. Okay, we would expect as we move it further away, we give it more gravitational potential energy, therefore we take away its kinetic energy. Okay, that energy has to be converted from somewhere. We can't just create it out of nowhere. Okay, so to move it further away, we change its kinetic energy. Okay, that's a little